Any other questions from you guys here at the start?
If you don't mind, could you go over number 1 on this same set of homework?
Sure. Hiker, this one,
Yes, sir.
hiker starts at camp while exploring, goes in a bunch of different directions. So first we've got some distance, bless you, some distance north, followed by some distance east, much more distance. And then a certain distance at an angle 30 degrees north of east. So like this, followed by south. So something like that. And the question wants to know, I will also explain, I'll point out, whenever WebAssign asks something like this, explain, you don't actually have to give it an intelligent answer because it can't grade an intelligent answer. So you could just write anything and you get a free point. You should still think about it though. But what it wants to know is the length of the green line and the angle that it points at. So to do that, vector addition for all 4 of these. But for that to work, you are going to have to figure out the x component and y component of that one that is slanted. Yes?
I have a whole different question.
Okay. Sorry, words. Does that feel okay for now?
Yes.
Okay.
Thank you.
You're welcome. Other question?
On the chapter 1 and 2 homework, the last question, like part C, I don't know if it's a glitch or something. Like when you have to write the formula in like terms of G and T.
Yeah.
I'm glad you asked because I forgot. I meant to show this to everyone and it slipped my mind. This one?
Yeah, but just the speed part, I can't get it to accept the answer.
That is because whoever coded this decided it needed to have absolute value brackets in it.
What in the world?
And again, machines are dumb and they don't understand context. They can't think. So if you haven't done this one yet, you can just copy it down. I would remove this question just because of how annoying it is. If some people hadn't already done it, I don't want to take their points away. So if you haven't done homework 1, number 14 yet, take a gander. There's no red numbers here, so everyone has the same answer. The issue with part C is, the main thing is that gravity and the initial velocity point in opposite directions, but whoever coded this decided that it needed absolute value brackets. I guess because, yeah, it asked about speed, and speed is directionless, so that must be why. Yes?
Did you read them?
Oh, yes. You know what, I'll write them too, because it's just hard to see. Absolute value bracket, V subscript 0 minus G, why is my marker dying? That's not helpful. Absolute value, V subscript 0 minus GT and absolute value. And this is just the straight vertical line on your keyboard. Alternatively, you can use the input tool to add the absolute value symbol. The last one is the same as B, thankfully. That's supposed to be 2. Yes? The lab? Oh. It's probably locked, but I can let you in after lecture. Wait, what'd you leave in there? Ah, no, you need that now, yeah. All right, let's go get that. formulate any other questions that you have, and then the rest of the things we're going to be doing today is ending chapter 5.
More question. Oh, you don't have on what?
Oh, the first one. It was like a similar one with like writing an equation. It's part C. Yeah.
All right, how you guys feeling? Any other questions on your mind for right now? All right. Let's see. Suppose that was it. Main thing we're going to do today is close out chapter 5. I want to do at least one elastic potential energy example, and we're just going to add one last formula onto things before we close out all new information before the test. I'll go ahead and point out though, on Brightspace we have a tab dedicated for test review. The tab itself has a list of all the things we've talked about so far, and there is already a practice test uploaded there. Totally optional, but if you want practice and you do this and feel comfortable with it, you will be more than fine on the test. I always make these both longer and more difficult than the test itself, because I'd rather you make mistakes here. Test is already written, test is 9 questions. This is like 11 math questions and then 5 concept questions. So, again, longer and more difficult. So if you can do this, you'll really be good for the test itself. And totally optional. I'm gonna upload an answer key today, and we can spend Friday going over it as well as any other questions leading into test time. Yes?
Will your answer key show the work or just show the
They
answer?
will. Yeah, I'm going to physically print it out, do it, and then upload a scanned copy. How you guys feel? Alright. Now, as I said, objectives for the day. Let's look briefly back at elastic potential energy. We talked about this, and if you've had lab this week, you utilized it at least once. So let's get a little bit more practice for it into your notebooks. To briefly review, this is a third type of mechanical energy. It is energy that is stored in an object's ability, well, not even in the ability to. It is It is energy stored in the object's current deformation / stretch. If an object is elastic, meaning that it can deform and then go back to normal by itself, energy is stored in it while it is deformed, and that energy is released when it goes back to normal. And you have noticed this whenever you have used some sort of a spring or rubber band as a slingshot. Because you deform it, the energy is released, and it becomes kinetic energy inside the projectile. EP is equal to 1/2 times spring constant times delta x. I keep forgetting to change that graphic. Which is 1/2 times spring constant, the strength of the spring, times the current deformation change in size of the object. Not final size, change in size. And likewise, spring constant also can inform you of the force that a spring is currently exerting in order to be at its current level of deformation. Talk about that one in a sec. To demonstrate an example where this sort of thing might come up, we are going to chuck a brick at a spring. This might not be a scenario you have physically encountered, but physicists love to use this as a hypothetical example, because springs don't really exist in nature, so we have to make up our own. This is going to begin with us launching a box across the ground at a spring. So it is sliding along the ground. The spring is currently in its natural shape. You can kind of think of this like a bumper, basically, some sort of a security feature to keep it from just crashing into the wall. And this is going to be our before state. We've launched the box. It is heading towards the spring. The spring is currently in its natural state. What type of energy exists in this before state? Say again? Well, what is currently happening in this before state? We've got a stationary spring and a box that is moving. So what form is all the energy in right now? Kinetic. Very good. The box is moving. That's really all that's happening in this before state. So right now we've got a lot of kinetic energy and nothing else. Now, as this box eventually collides with the spring, what's going to happen? Okay. The spring is going to deform by some length. Its length is going to change by some amount. And because its length changes, it is going to have some amount of EPE stored inside of it. Now, as that is happening, what is going to happen to the box? Sorry, a little louder.
At that moment, it's at rest, so there's no kinetic energy.
Okay. For a split second, the box is going to come to rest. And this happens, like, the spring might be a little hard to visualize, but the same thing happens if you just throw a ball at the wall. For a split second on impact, it stops, right? And in that moment, all the kinetic energy it had is now stored as EPE. And then a split second later, it's going to bounce back because EPE, like, elastic objects always want to return to their normal shape. It's why you have to literally force them to change and then keep them that way. If you let them go on their own, they return to normal. So you throw a ball at the wall, it'll temporarily warp and then spring back to normal and kick off of the wall. Here, if we unpause time, the spring will return to normal and launch the box away from it. But for a split second, the box does stop. And that happens at the point where the spring is at the most changed, where it is most compressed. So this brief freeze frame is going to be our after state. The point in time where the box comes to a stop and the spring is as compressed as it's going to get. And we're going to do some calculations to just show the transformation of energy throughout the process. Any questions on the physical setup before the math? Feels like all of my markers are about half dead today. Probably got the most ink. So, first question, how much kinetic energy does the box initially have? So we'll use the formula with its initial velocity. So 1/2 times its mass times its initial velocity squared. And that should give us, please correct me if I'm wrong, about 20 joules.
$19.97.
19.97? Is that what you said? Okay, thank you. So that's the box's total energy level before anything else happens. That's just its energy level sliding across the floor. Something had to do work to give it that energy. And what's going to happen to that energy as it hits the spring? Very good. Let us consult conservation of energy just to watch that happen. Initially, we've got some amount of kinetic energy and a 0 amount of EPE because the spring hasn't compressed yet, but I'm going to list initial EPE here for completeness sake. On the final side, all that kinetic energy is going to go away. So this being our final state, at that last moment, kinetic energy will drain to 0, and all the energy has to be stored in a different form as EPE in the spring. So we got the energy levels changing from one form to the other, from one side to the other. Initially, we've got about 20 joules of KE and no EPE because the spring hasn't compressed yet. It's in its original length before impact. After impact, the box's velocity drops to 0, so it would have no KE left, indicating that all of that energy has now transformed into the kinetic state. And since we know the change in length of the spring, it's delta X, by knowing how much energy absorbs to cause that deformation, we can figure out what its spring constant would need to be for that to happen. How tough this spring is in this particular scenario. Questions so far? Yes.
Where did we find
This one?
Yes.
Yes, that is the spring compresses it a total of 15 centimeters. But we want meters, and so 15 centimeters converts to 0.15 meters.
Excuse me.
Any questions or issues with where I've currently left it? Alright. I'm gonna take it over here and simplify it a little bit. Get rid of all the zeros. So, EPE initial was 0, KE final was 0, so I just got rid of those. So now we've got KE initial equals EPE final, showing again the transformation from start to finish. We can figure out what the spring constant of the spring must be for it to deform this much when absorbing this much energy. So K would be 19.97 over 1/2 times 0.15 squared. And if you put that correctly into your calculator, I will double check that answer, because I've been rounding all day. $17.75 newtons per meter is the unit for K. That is because it measures how much force is required to stretch something by 1 meter or compress it by 1 meter. So, if I was to take this very same spring, rip it off the wall, and physically try to stretch it with my own hands, it would take 1775 newtons for me to try to make it 1 meter longer. I'm not doing that. So this spring might be of the tier rated for car shocks, as opposed to, say, this thing, whose spring constant is far closer to like 5 newtons per meter. It only takes 5 newtons to make this 1 meter longer, or something to that level. So that is a very durable spring. Maybe not exactly car shock quality, but far closer than this one is. Any questions arriving at that number? Excuse me. Okay. Now, spring constant is useful because it can tell us one other piece of information. If we look at that after state and unpause time, what's going to happen to the spring end of that box? Yeah, it's going to sproing back. Sproing is a highly technical term. And it's going to be pushed back, not only because the spring has a bunch of stored energy that it wants to release, the box is going to be pushed off from it because when a spring is compressed, or when any elastic object is deformed, not only do you have to exert force on it to get it into that form, you have to exert force on it to keep it in that form. And likewise, because of Newton's third law, it is going to be exerting force back out. So when you compress a spring, or again, anything elastic, it will push back. And if there's nothing else keeping it there, that outward pointing force is gonna push everything back out so it can go back to normal. It's literally fighting to return to its normal shape. And we can use spring constant along with that other formula from the previous slide to figure out how much force the spring is currently exerting while it is deformed by a certain amount, while it is extended or compressed by a certain amount. So Fs here stands for force spring. It's going to be 1775.1 repeating times the spring's deformation of 0.15 meters, and that is about 260 something newtons. Yep, 266, round that off. And so, the moment before the box gets launched, this is the force that is going to push it off of the spring. The spring will push back with this much force to get the box off of it so it can go back to normal. All elastic objects do this, and this is the force that causes things to bounce, really. You know, throw a ball at the wall, it'll pancake for a split second, but because it's compressed, it's going to exert a force against the wall to go back to normal, and so this is the force that then kicks it back off the wall. The reason it's negative is just because springs always exert a force in the opposite direction as the deformation. If you compress something rightward, it pushes leftward. So Newton's third law, same force, opposite direction. That's why that negative is there. On the other slide, it's still here. How you guys feel? Okay. Now there's one more very brief concept I want to cover before we close out chapter 5. It's not a long one, but I want to show it to you today, and then on Friday we can review everything and make sure everything gels nicely before the test. So we're introducing it today. It's the very last new thing before the test, very last one, I promise. And that is the physics notion of power. This is a slight modification to the work formula, so this is not all new. This is a continuation. Power is one of those words that is used pretty often in the English vernacular kind of separately from its physics definition. And before I define power from a physics perspective, I want to go back to the physics definition of work very quickly. Work, and the formula for work, is force times displacement. And it's a useful formula. It tells you how much energy a certain action is likely to take. But there is a problem with it. And it's that this formula does not at all reference how fast something gets done or how easily it gets done. According to this formula, I would be as impressive as a tractor if both I and the tractor can exert the same force and push something the same distance. If I, not very powerful adult human male, was to try to pull something across the length of a football field, this formula would give me the same work output as a machine so long as I'm exerting the same force over the same distance, regardless of the fact that after the whole ordeal, I will be sweaty, miserable, and collapsed, whereas the tractor will probably do it very quickly and not notice. This formula is flawed because it does not take into account any of those things. This formula is how we take those things into account. Work is the energy used up, the amount of task performed. Power is how quickly it is done, how easily it is done. The formula for power, capital P, is work over time. It is the rate at which work is performed. The more quickly you can get your work done, the higher your power output is as far as physics is concerned. So again, the rate at which work is performed, and that's why the formula is work over time. If you can do something in a short amount of time, that will increase your power output. Whereas if something takes you longer and you're dividing by more time, your power output drops. So power is a new variable. As such, it comes with a new unit. And in physics, we measure power in units of watts. I trust you've heard that unit before. Have you only ever thought of it as exclusively an electricity thing? I would not fault you for that. It's not just an electricity thing. However, its use in electricity is correct. We actually use it the same way that they do in electricity. If you go buy like a 30-watt light bulb, what that tells you is that light bulb needs 30 joules of energy every 1 second to stay active. That bulb then does 30 joules worth of work every second. So 1 watt is 1 joule per second. And all machines, including, mechanical human movement, has a certain power rating. You need a certain amount of energy every second to keep performing a task. And so all machines, when you buy an appliance, the power rating is usually written on there somewhere, and that tells you energy per second for it to remain on doing its job. So there's a couple of different ways to think about power. It's the rate at which work is done. It can also be thought of as energy cost per second. So the higher power rating something has, the more it's able to accomplish per second, but it also drains more energy per second. High power actions and high power appliances drain energy very fast, which is why you want low wattage light bulbs. They do not drain energy very fast. Watts is the metric unit for power, but there is another unit that is commonly used in America, namely the unit of horsepower. You probably hear that most in car commercials. 1 horsepower is approximately, I don't know the exact ratio memorized, about 750 watts. So if you can figure out your own wattage, you can also figure out how many horsepowers you can output. That said, fun fact about this unit, 1 horsepower is not actually the maximum power output of a full-grown horse. It's not based on grown race horses. It's not even based on grown draft horses that are known to pull very heavy things. This unit, the baseline for 1 horsepower, was historically determined by mine ponies. Ponies that would pull coal carts in mine shafts. You had to use ponies because a full-grown horse wouldn't fit in the tunnels. Also, not only was it, not fully grown, it also probably had black lung. So these were not very impressive horses. So just a historical footnote on that particular unit. If a car commercial tells you how many horses that the machine is equal to, it's not. That's how many sick ponies it's equal to. Be accurate in your advertisements, Ford. Anyway. So in physics, we use power to determine work per time or energy use per time. There is a second formula that I haven't acknowledged yet, and it's really just the same formula again, just slightly altered. Power is work over time. The work formula is force times displacement, which means power contains displacement over time, and displacement over time is velocity. So it is the same formula twice, but sometimes you may want one version or the other. And what the second version means is, if you are pulling something at a velocity, you can use that to find your power output as well. So like say, a tractor exerts 100 newtons forward and pulls something forward at a speed of, 5 meters per second, you can figure out the wattage of that task. This is the version that, car and truck manufacturers use most often. But it's the same thing. You can use basically the same information either way. Questions thus far? All right. So the last thing we'll do is just get a very small amount of practice for these concepts in your notes. We're going to figure out the work done by and the power output of two different people carrying two different boxes up the same flight of stairs. So person A and B each have two differently sized boxes. One weighs, these are weights, not masses. One weighs 1,000 newtons, the other weighs 500 newtons. And these two people are going to physically carry them both up the same flight of stairs, 30 meters in height. Even though you do walk forward when taking stairs, the force you're exerting upward is parallel to the height. So when you're climbing stairs, the bulk of the work is specifically vertical axis. You're exerting force up, and you are displacing up. So we're just going to look at the vertical variables for right now. So each of these two people will do different amounts of work. Person number one is carrying the heavier box, so they're going to exert at least a force of 1,000 newtons to get it up the stairs. And they're going to carry it up vertically upwards 30 meters. So the vertical lift on this flight of stairs is 30 meters. That is what I said, right? Yes. Now, again, that vertical force is parallel to the vertical displacement, so that's why we're only looking at the upward things here. We're not trying to also figure out, the forward on the staircase, because it doesn't matter for this calculation. We're just looking at upward force and upward traversal. And that means person one is going to do a grand total of 30,000 joules worth of work, which is a lot. That's several slices of pizza. Person two is going to carry a lighter box the same distance. They're using half as much force for the same distance, so they're only going to have half of the work done. So 500 times 30 is 15,000 instead of 30,000. So strictly in terms of work accomplished, person one is getting more done than person two. They got a heavier box up the same distance. But as stated earlier, that's not the end of the story, because the work formula does not factor in things like speed or how easy something was. And so now we're going to factor in speed and find the power output of these two people. The first person's power output is going to be their work over time. They got that heavy box up that stairs in 1 minute or 60 seconds. So their power output will be their work done of 30,000 divided by 60 seconds of time. That's a power output of 500 watts. Person two did half the work, but they also performed the task in half the time. Half the work over 30 seconds instead of 60. So despite getting less done, these two people have the same power output. And technically, their feats were equally impressive. They have the same power output. These are both very good athletes. So, a takeaway from this is that strength is not the only determinant of power. Speed is equally important. Sometimes getting something done fast is as or more important than just punching hard. Questions? All right. That is the last new piece of information for Chapter 5. So let all that digest for the day. On Friday, we'll answer any questions you guys have about the information we just covered, look over the study information and practice tests, and make sure everyone's feeling ready before next week. Let me know if you guys need anything, and have a nice day.